So now if you print dots, so if you print it out, you will see. So now I have a function that is of type A to B to A and B. So this is the type level. The program is just a function from HA and HB to conj of HA and HB. And conj is the constructor for this AND type. So AND is a type with only one constructor, with the conj. So at the type level you see this, at the program level it uses the conj. Then, so the same, and so for you've also, so the same thing works for OR, but OR is actually, if you look at the logical OR, the OR is actually again an inductive type, but there are two ways to construct the OR. You can either say, well, either we go from A to A or B, or we go from B to A or B. So these are the two introduction rules. So OR being the type that is, so there are two ways of constructing an OR type, disjunctive type, either by using its left side or its right side.
So the vertical bar is the meta version.
Exactly. These are variant.
Yeah.
This is variant type. Yeah, that's basically what it does. So again, if you look at this, so if I prove A and B implies A or B.
It's a variant type which had the bug, right?
Yeah, but don't worry. There's only two of them, so it comfortably fits in 2 bytes.
Yeah.
An OR with 255 variants. Yeah, that's really not. So I introduced the hypothesis, and now obviously the first thing I have to do is I actually need to, so because this is now an AND AB, so I actually know that this is a type, so I need to I can destruct this type because it's a type that contains two other types, a value of types that contains two other types. So I destruct my HAB. The language kind of breaks down here, but so I destruct HAB, and this is a way of saying, okay, so HAB will turn into two hypotheses, and I'd like to name those HA and HB, which is exactly what you see happening here. And then, so in this case, I did to construct a value of A and A or B. I have two ways of doing that. I have two constructors, namely the OR intro right or the OR intro left that we just saw. So basically, I can also just say, so there is a tactic which is called constructor and then with a number. So basically telling you use that particular constructor. So if you use constructor 1, it will tell me, okay, fair enough, you need A. And left is basically a sort of an abbreviation for that. So left or right, because that happens to work with the OR really usefully. And then you can just use exact HA. So again, it's just, and if you look at that, you can see that. So it actually, what it does, this matches my, so it's a function from HAB, which is type A and B. So it breaks down HAB, which it can only do in one way, namely conj HA and something. The something is not important. And from that I return the OR intro left HA. So it's a program that goes from A and B to A or B. A or B gets broken down by pattern matching, HAB. I remove the HA and put that in OR intro left. So I use that to construct my OR type. And this is the whole, the proofs as programs approach. You have a type and you construct a program. Obviously it starts getting more and more complicated, but this is sort of the basic approach. So another one, so this is an example of how you use the OR elimination rules. So this is just a general OR, so A implies X, B implies X, A or B implies X. This is just a general OR rule. So if I do that again, and now I will, so the first thing I'm going to do is I'm going to do a case distinction on either A or B, which I do by destructing it. And now I will in the end get 2 goals. So I use so this is the tactic language here. So I use this, the bar, to say, okay, so one part of my goal, the first goal I'll call HA, the second goal I'll call HB, or at least I need to, I just noticed the light starting to flash and I was slightly too late. So it's that's the way it.
So it's shutting down.
Yeah, exactly. It's my battery is gone.
Yeah. I was chatting with some of your theory colleagues this week about theses, so bachelor's thesis students.
Yeah.
And do you have any bachelor students doing theses in CoC?
No. Well, maybe.
Maybe. Okay.
But,
so is this? I mean, I'm sorry, I'm falling asleep here. Is it interesting? I mean, why don't you have students going, no, this is great, let's use this?
Well, the thing is, so it can definitely be interesting. I think the point is that because this is the incredibly trivial stuff, right? That you sort of need to start it, which is so there's the learning curve is
it's
quite
really because I
steep.
didn't sleep well last night. It's not your
Fair enough, but it is not the most exciting stuff in any case. That's definitely true. So the thing is, you need, in order to get to a point where it really becomes interesting, where you start verifying programs and doing interesting things.
So what's interesting to verify? What's one of the things that a thesis student could verify that would be useful for the world?
Well,
I mean, obviously, I have to figure something out. So
yeah, that's so for example, what I did for my master's thesis, so that would be is have a very to add to CoC a way to automatically, so without you just type auto and it works basically, to automatically verify very small proofs. So you have, so for example, because if you have something like for all natural numbers under 24, something is true, you can basically, that's something you can just automatically compute. But again, it's so this is they're all and if this is this could be the start of something really interesting, because for example Gontier uses this specific method also for far larger proofs. But it's difficult to find very small bits that either haven't been done yet or
are simple enough
to play around with. Yeah, exactly. So obviously one thing to do is to sort of take an existing library and add a few bits to it. For example, one of the things that we are doing for the quantum development, at some point we'll need the tensor product of matrices. So that's something that's
yeah. I actually wrote a library, but also the important thing is to do partial trace.
Yeah.
But do you want to verify a simple a linear algebra problem? Is that what you're looking for? Is that something you could do?
That would be, yeah.
So if I have linear algebra is going to multiply 2 matrices that are less than 5 by 5.
Yeah,
that
could be.
I could prove that, and that would be a useful thing, and no one's done that before.
I don't know enough about the linear algebra and CoC to say whether nobody's done it before, but something in that.
But even if no one has done it, someone has done it before. Having a student actually do that is an interesting thing for them to do.
It would be, yeah,
right?
so certainly. So either taking simple problems like that, or sort of taking one specific small theorem and adding that to a library. So for example, implement a tensor product, prove a few properties of that,
so
that kind of stuff.
Roman's written a library, but you can verify that it's correct, as opposed to probably filled with bugs.
I wrote it in
Yeah. Okay. So.
And he's written it in Lisp, so it should be easy to prove, right?
Yeah. Exactly.
No, really? I'm making that up. Is that true?
No.
Is it easy to function
what you do is you re-implement it in CoC probably and look at that, but that shouldn't be too difficult because Lisp is kind of a functional language as well.
No offense, Dave.
You can say int. You can say int and name variables, and you can have classes, so you can have types. Though that's types in the programming language sense. I'm not sure if it's types in this sense of.
In one of the senses of this, it probably is, but yeah, it's.
So the practical reasons why you would use this over, say, I mean, for that example you gave for multiplying, possible numbers below 24. Is there some reason why you wouldn't use a resolution theorem prover for that?
This can do, because the thing is, this is interactive. So the problem with automatic theorem proof is always you're of necessity you're limited. So you never know you're very limited.
So I understand tactics in that context, which are sort of broad strategies for
So
use
the,
of
because the
whatever,
idea of this is basically that you have tactics that basically work as a resolution theorem prover. So you can sort of say, okay, you know, auto or resolution, and you run a resolution theorem prover on your problem. But of course, a resolution theorem prover cannot solve everything. So here, what you could do is sort of what you can do is if you have at the high level you start dividing up your proof into the different bits that you have. So the high level proof, you start breaking down your proposition into its constituent parts, into its lemmas and whatever. And then for the appropriate bit, so okay, yeah, this sub part of the proof tree I can prove with a resolution improvement, so I do that. This other part I need to do manually, this other part I can use another strategy for. So you can, in a certain sense, it's exactly that. You have manual input as much as you need it, and the bits that can be done.
Is it helping you though to determine which parts of the problem are modular in that sense? In that, you know, this is best tackled by breadth first resolution for improving
no,
this part.
It can't tell you that because that's just experience. But it's. But that's the main thing. So it allows you to guide the development in a certain sense.
I mean, you could always assert new axioms to force resolution theorem proving down some particular.
But the point is, this in this case, that's actually integrated in a certain sense. It's integrated into the language. So it's much more, and it allows you to use multiple techniques as well. That's I think kind of the
So about these tactics,
Yeah.
you have to know this tactics, or do they add some built-in tactics?
Yeah, so exactly. So there's about 100 of them, but most of them are only for very specific cases. So you've got about 20 core tactics, and yeah, there are ways of manipulating your proof. So I mean, and that's what you do. So you have very specific tactics, for example, that would run a resolution theorem prover, or if you are there are, for example, tactics that there's a ring tactic which resolves algebra, that kind of stuff. So there are specific tactics for specific purposes, and there are just sort of administrative tactics to break down proofs or
So this is a library you can add to. There are certain core tactics.
You can write your own tactics, of course. That's because at the end the proof checker is just run. So your tactics don't necessarily need to be correct, because there's always the proof checker, and it will call you and say, yeah, listen, this is not a valid proof.
So you have access to a Galena interface, because I guess tactics are written in.
So there is the tactic language, which is a scripting language for tactics. So you can already do a bit of that. But it is also and that's where it really becomes interesting. You can actually write plugins, but then you're writing your tactics in OCaml basically. So you have access to all the data structures of Coq, and but that becomes very bloody and yeah.
Actually, I wanted to ask something. So, are we in kind of discussion already session?
Yeah, we haven't passed the hour.
Yeah, so I
yeah.
just wanted to ask this during the talk. So, I can see that what you do, you have let's say propositions. You convert them to types, and then proof becomes equivalent to program. Of course, that reminded me the fact that, of course, we had type theory developed. At exactly the same junction when there was a Zermelo-Frankel and Choice axiomatic theory or set theory, and most mathematicians are happy with ZFC set theory, and they know about type theory, but nobody really uses it to prove. So human mathematicians, they would just use set theory, or effectively set theory, and then of course this implication A implies A means that A is a subset of itself. So I wonder, would it be possible, or the reason they go to type theory and proof, is there any reason why you cannot do it with sets, or
I don't know. I think the point is that if you do it with there are a lot of type. There are other theorem provers that do these things in different way. I think the reason they've used type theory for this is because that it gives you the largest possible amount of things that you can prove. It's the most extensive. So I think that if you use set theory, for example, you'd have a different it's probably more restrictive from.
Isn't that why people do proofs in topos?
The ZFC is really rich, isn't it? I don't know. I think there's always discussion whether you have choice axiom or not, but
because that's also the point. So that's why you can use this rich type system, because you don't need it to be decidable at all, because you always have user inputs to sort of help you pass the difficult bits. So in a certain sense, you are literally being your own type, well, not your own type checker, but you're being your own type constructor in a certain sense. So if it and so maybe with set theory, which is slightly less rich, you might have a point where it's where it becomes decidable, but it also means that you're less expressive. So that's the choice you have in a certain sense. It's expressivity versus decidability. And in Coq they're definitely going, so we want to express as much as we can, and if the user has to help along a bit to keep it decidable, well, so be it. That's the choice they've made.
It's not a matter of degree, though. It's just a hard threshold.
But
introduce some type, and you've increased expressibility, but at the expense of provability. But it's an all or nothing thing, I guess. It's not a spectrum.
But in this case, they've definitely gone for expressivity.
But there's also the fact that type theory is constructive. So you don't use set theory because you want the constructive feature.
That's definitely.
So you don't use axiom of choice.
I don't remember. Yeah, you can add sometimes. It depends on what you're doing. You can add something.
Because all
for example,
built in.
For example, one classical thing we have seen is the type prop. The type prop is a type containing special types which are proposition. In that kind of type, you have the proof. How do you call it? I can't remember. Anyway, any two inhabitants of a proposition. A proposition is a type, so every two inhabitants of that proposition are equal. But if you choose not to use prop but other types, you can have many different.
So what you're talking about is proof irrelevance.
Proof irrelevance.
Exactly. So there are exactly. So and it's like the axiom of choice as well. You can sort of there are things that aren't there by default. So the axiom of choice, for example, you can choose to define that for either certain sets or in general. I think in general it's not that. The same thing is proof irrelevance in the sense that if I have two inhabitants of the same type, so basically two different proofs of the same proposition, are these proofs actually equivalent or not? So that's basically proof irrelevance, which is also
thing, but it's a classical feature you can add in type theories. You don't have at the beginning, but you ask.
So in a certain sense, you have the basic calculus, which, as far as I know, doesn't include the axiom of choice and doesn't do proof irrelevance. And you can manually define these as axioms if you want to, so you can sort of extend these.
Just when I have this usually constructive mathematics usually understood when you don't have axiom of choice. Because the axiom of choice, you have all the existence theorems.
Exactly. So it is. It is definitely it's constructive.
And this is also equivalent to. Well-ordered sets, for example.
Again, so this depends on your definition. So generally, a set is literally just a set, and well-ordered. If you want to add that as an axiom, that's of course possible.
Are you going to show us any programs?
I can do a quick. I can do a quick. Well, maybe that's as a sort of tool to. So just do a quick actual proof of an actual program, something very simple. That might be if we can get that.
While it's loading, the reason I asked this is I'm just thinking, I'm always tempted at some point to take Common Lisp and implement some basic proof checking or something. Because I sometimes want to verify some of the mathematics I do.
Isn't ACL 2 or 3 implemented in Lisp?
What is ACL?
ACL is a theorem prover as well, and I think that's actually implemented in Lisp.
It is.
I think it's the Association for Computational Linguists. Sorry.
So, maybe you should just use that rather than.
But I don't want to go to a very low level in the sense to basic axioms, because I want to go just a little bit, for example, work with inequalities. I have, let's say, 10 or 5 objects, some functions, and I know there are inequalities between them, and I just want to see what other inequalities follow for them, for example. And simple things like that. But that's I'm worried that if I start doing things like Pop or Isabel or something, it will just take me, it will consume completely. It would be easy for me just to by hand to do all the combinations.
Look, that's basically been, that's why I'm here. That's how I got into this situation.
You got suckered into it years ago
exactly,
and you can't get
out.
And
it consumes you. I started out being interested in, grammars and parsing and all that, and then I met Herman Geuvers, and now I'm
ACL, man.
Yeah. So it's so don't follow don't do it. Just forget you were here.
I'll talk about grammars and parsing with you if you want. Anytime, come on down.
Oh yeah, ethics grammars. I really miss that every once in that kind of stuff. That's that was cool. But anyway.
Covenant binding theory, man. That's what it's all about.
So, for example, one of the things. So, this is an actual program that you can prove. So there's an extension to COP which is called Program, which basically does proof obligations. So what we have here is we write a function that so this is an actual COC function rather than so just have a function that divides by 2. So we take a number. We, if it's the successor of something, well, we return the successor of, and then recurse. So if it's not the successor, we return 0. So this basically is a very simple way of dividing by 2. So now the way this works is
very simple way of dividing.
Well, simple in the sense that it doesn't require about 16,000 other definitions, but yeah. But the thing is, we're actually going to prove that this works. So that's the fun thing. So it's a function that takes a natural number, so an n, and it returns a natural number, but not just a natural number. It returns an x, such that n is 2 times x, or n is 2 times x plus 1. So we end up having the right program. And the thing is, so what COC does for you is basically, so it runs this. And so the thing is, so in order to construct this value, you actually need to provide a proof of this. So if I want to construct a value of this type, it's a dependent type, is what they call it. So it's not just a net; it's a net with a value added, and this value is going to be a proof of this particular proposition. So there's an extension program which basically takes care of all the administrations for you, and basically just sort of calculates all this and just gives you a few proof obligations that you need to solve. So for example, we can look at the first obligation. So basically, so it needs to, I need to tell me that x plus 0, P is x plus 0, or P is x plus 0 plus 1.
It could be x
plus
plus
1.
x plus 1.
Yeah.
Plus 1. So yeah, this is the, so it basically, yeah, so so yeah. So this is the this is not what we're proving. This is the hypothesis. I'm kind of my brain is starting to not work anymore. So yeah, basically P is x plus x, or P is x plus 1, and then I need to prove the fact that P plus 2 is x plus 1 plus 1. So basically a load of successors.
So how is that hypothesis generated again?
So basically, well, you can, if you do it without the program, we can show how that works. So basically now it's basically then, yeah, this is not going to work because I want something that's both a type and a proof. So in this case, I basically have to write the proof term by hand, because what I need to suggest, what I need to put in here is exist 0, and then here I need to write, and I need to add at this point a proof term of the fact that this 0 obeys this particular this. So because so this is depends. So this type is basically you have a value x of type not coupled with a proposition, and the thing is, in order to construct a value of this complete type, I need to prove the value plus the proof of this proposition given that particular x. So if I want to construct a value of that type, basically I need to create a proof term. So I say exist 0, which is my value, and then at the point of the underscore here, I would need to write the actual proof term for the fact that 0 is 2 times x, or that kind of thing. So what program basically does, it sort of takes care of these things automatically. So it says, yeah, okay, you've written 0 here. So it tries to generate a proof term automatically as far as it can. But if it doesn't succeed in doing that, it tells you, okay, you need to do it yourself. So what happens then? So if I put in the program, there we go. Oops. So basically, so at some point it tries to generate a proof term, and it notes that, yeah, at here's where it breaks down, and this is a bit you need to do manually. So we start by destructing the OR here. Okay, and now it's basically, so here you can obviously, if P is x plus x, then the successor of the successor of P is the successor of x plus the successor of x. It's basically what it's saying with a lot of pluses and brackets. So I just use the left bit of the OR there. I rewrite, because I can replace P here by x plus 0. And then I use a lot of axiom wrangling. So plus n0, for example, if you can look at that. Basically an axiom that tells me that, okay, that's the proof term. Let me use check because that's the name for it. So check just shows you the type, so plus n1 is basically saying for all n is equal to n plus 0. So I rewrite that in the other sense to replace n plus 0 by n, because I've got an x plus 0 here. So that basically gets replaced by x. So you'll see that happening. Then I use plus nm, which replaces the s of x plus x by x plus sx. And now, so again, it's just an axiom, and now I've got the same on both sides of the equality, so I can use reflexivity. The right is basically the same thing, so I rewrite a lot, rewrite more, and then at some point I end up with something that's equal. So this is basically just applying existing axioms of natural number. So for example, the fact that n is n plus 0, or so if you look at plus n as m, basically saying that n plus m plus 1 is n plus 1, with the brackets in the right place. And then I've got reflexivity again. And then, so that's okay, defined. Now it tells me, so I've still got 3 obligations remaining. It tries to solve some of them automatically. That doesn't work. So I'm now going on to the next one. So again, I do some stuff. So here at some point, so this is actually a much simpler obligation, because here I need to prove that basically n is not 2 or higher, and then n is 0 or n is 1. So if n is not the successor of something, it's either 0 or 1. So now I do this by induction on n, or sorry, by case analysis on n. You run this, yeah, sorry, I'm not trying to go into too much detail here, because otherwise... and then at some point QE. So now we'll see that I've got 2 obligations remaining. Again, so now it tries to solve the obligations automatically, and the third and fourth it can now actually solve by itself. So it does that, and no more obligations remain, diff 2 is defined. I think we can actually look at 3 and 4. So what I was trying to prove here was, okay, it's so you can see that these proof terms get very complicated. Yeah, definitely get very complicated. So
it's a good thing it managed to do it by itself, right?
Yeah. Well, if you try to prove it, it looks slightly better. But yeah, this is so.
Slightly better. Because if it hadn't, then.
Yeah, well, then again, I mean, look at obligation 2, which was one that we were solving ourselves. It's not as if that looks any better, right?
Okay.
So it does present this in a reasonably nice way. This is the point why this program extension is so nice, because if you have to write this stuff for yourself, Andrea Sperti manages to do this apparently. He can actually write proof terms sort of without using a tactic language, which I've always found weird, but yeah. But anyway, so that's basically what Coq tries to do. So it tries to allow you to do the things that you need to do for yourself, but everything that can be done automatically, like solving these things and rewriting them to look nice, it does. So it's kind of the nice balance between human interaction and automation, is I think the word. So yeah, and that's basically my my day job.
So if I found this, it's generating. So it's it's sort of running forwards, and then when it requires you to resolve some particular action, which generates. So then you put this in as an obligation. In other words, you're committing to some additional axiom.
Exactly.
The resolution of it. Okay.
That's basically what it does. Yeah.
Okay.
Okay, so thank you.
Yeah. I wish the theory of this were easier to explain. Because you do get sort of